Hello everyone, we are starting a free open lecture in our Discord. All our lectures are held weekly without interruptions. If you, the viewer, want to ask questions and receive answers in an online format, join our lectures. You can find the link to Discord in our Telegram channel. To find out the exact time of the lectures and join our official Telegram channel. Otherwise, if we have a right shift by exactly 2 bits, then these two ones will move over here, TFSPE, and these first two, they just got erased. And that is precisely the essence of the logical shift. There is also an arithmetic shift operation. It is basically the same as a logical shift. In a shift, in my honest opinion, to the right or even left. In the opposite case, it will be cyclic, with the first position serving as the sign. Complexity is not needed right now. So accordingly, what will our recurrent form be? If the current cell is occupied, then we adjust the bit mask, which means that after processing this specific cell, we will end up with not 1, but 0. This adjustment is crucial because it ensures that we are precisely subtracting the bit mask. By doing so, we maintain the integrity of the data and ensure accurate results in our computations, and we immediately and swiftly move to this specific cell, simply and straightforwardly passing the value that we had read before. We do not increase it in any way or manner. If the board can be placed in a horizontal position, then we effectively add 1 to the mask at the position of G plus 1. This means that the mask is updated to reflect the new placement, ensuring that the board's position is accurately recorded and accounted for in the overall configuration. In this case, it actually does not change in the currently occupied position. And we definitely add as the value what we have read up to this point.
Want to become a great programmer? Subscribe to our Telegram channel.
If the board can be placed vertically, then we will have a living position becoming 1, while J plus 1 remains unchanged. We were just explaining how they transition. This case is described in detail. TFSP, the starting value in the matrix with optimal values will have a 1 in the 0, 0 position, while all other positions in the matrix will initially be 0, and the optimal value will be calculated here. The complexity of the solution will be m times n times 2 to the power of n. So how would this look in the code, for example? That is, we initialize our address and set the start to the value of 1. We carefully iterate through both hedgehogs and masks. We thoroughly check the case when the cell is already occupied. Then we move to the next position, and furthermore, we further attempt to place the board horizontally and vertically. Whether in code, Python, or Pulsar, a purely record-breaking formula will already be taking place. So, by the way, I almost forgot to mention one trick. It is the transition from one line to another, which is, in other words, when our current life ends, we transition smoothly to the next one. We will indeed have such a transition in place, which means that we pass the mask that was at the end of the previous line to the new line, so that we do not forget it. So there are questions about the solution, such as how it is implemented and its effectiveness, about the code, including its structure and logic, how the battle with masks works here, and the strategies involved. What is it all about? Several new techniques, like advanced algorithms and innovative methods, are used right away. TFSP? No questions? Yes. It's not very clear. It would be better to explain again what the point of using a mask is. Well, the main focus with the mask is to encode the state of the floor as zeros ones, to provide a detailed representation and ensure accurate data encoding for the system to process effectively. Well, or like Boolean values, a mask, which is usually bitwise, is why the zeros ones are stored like this. And here we have, for example, let everything be in zeros and ones, which means binary representation, where each digit is either a 0 or a 1. So here we have a floor, and everywhere there is a 1, it means that there are boards standing upside down. By the way, such a floor cannot be obtained. Let it be something more realistic. Let it be something more or less like this, in any case. Definitely. That is, as we have the boards, we can even show how they are positioned. Here is the board, here is the board, here and here. For example, actually. And here we are, let's say, in some cell like this one, let's say. In the cell with hedgehogs, let's say. This is the floor, and here we are finally in this cell, where we are trying to place the boards either vertically or horizontally. We essentially look at this mask to see if we can place a board starting from this cell. If there is a 0 here, then we can. If not, we cannot, and we move on. Otherwise, we place a 1, TFSP, right here, and either here or here. In other words, we are trying to place the board. This transition is clear and evident as we carefully check and meticulously observe how we try to place the boards in their designated positions. That is, the current state of the entire flooring is encoded using zeros and ones, and everything is built upon this. Then, after we carefully maneuvered it into position, we somehow managed to press it into place here. Ensuring it was securely and properly positioned, we took the necessary steps to make sure it was firmly placed. What is happening? What kind of battle was there initially with the mask? What did it encode? She carefully encoded a more pleasant and visually appealing color to take, ensuring that the new hue would be more soothing and enjoyable to look at. She initially encoded positions like this, meaning no, she didn't take this position. This means that the position she encoded was not the one she took. Therefore, we need to take another one to ensure accuracy. Yes, nothing has changed here. It encoded this position. We have 1 here, 0 here, 0 here, 1 here, 0 here, 0 here, TFSP. From this initial step, we move on to the next phase, which involves carefully placing a horizontal board. This board needs to be positioned in such a way that it aligns perfectly with our requirements. Specifically, we will have a 1 here, indicating a certain condition, and we will have a 0 here, representing another distinct condition. Here we will have a 1, in this example. Therefore, specifically, the mask for cell I, J, 1 will encode the pink positions, respectively. Because here we will consider everything before the pink as already fully filled. Everything after the pink is still completely empty. Indeed. Such transitional positions, where not everything is filled and not everything is empty, are encoded by the mask. Such a mask is called a profile, which encodes a transitional state where not everything is filled yet, but not everything is completely empty either. This is its main idea. Next, we will smoothly transition from various different ones. Here they are clearly shown for better understanding and visualization, where in the specific position of the battle, the mask will exactly correspond to some particular cell J, and precisely. That is, there will be essentially, indeed actually, a strict correspondence between column J and this 0, TFSP, and here it is. with this one, and so it will definitely, undoubtedly, and without a doubt continue in the near future. In other words, it will correspond with the number 40, and this particular value will also be encoded in the same manner. This is clear, right? In fact, it changes word by word in each work. Each position of this string will have its own unique and specific mask, which starts encoding from position ig to the end of the string, and the remainder from the second string does not reach position ig. This mask is responsible for encoding the characters starting from the specified position ig and continues to do so until it reaches the end of the string. Meanwhile, the remaining characters from the second string are not able to reach the specified position ig, thus they are excluded from this encoding process. These states will be encoded for the process of eg, and these masks can be anything in any conceivable form. That is, we have a total of, say, n columns. This means that the total number of possible masks is 2 raised to the power of n. That's how it is. That is, we are iterating. There can be all zeros, all ones, or they can alternate. We iterate through all of this and try to move from this position to the next position. For the cell ig plus 1, the masks will also be iterated, meaning that they will not be directly iterated here. We have some mask here, and we derive a new one from it, depending on whether we set something or not. And then from this mask, we will move further to ig plus 2, where it will also be updated.
Want to become a great programmer? Subscribe to our Telegram channel.